if we consider a simple charged object, and this object is in an external field, then we know that the force on the charge is equal to Q E external, and that will help us to set up and compute the dynamics of the particle by using Newton's second law. And so in that sense, a point charge in an external field, we can only talk about forces. But what if we have an extended distribution of charge? And let's consider a very special case where we have a positive charge and a negative charge. And let's imagine that these charges are fixed together with a massless rod. So that way they will move together. And let's put this object in an external field. So we have an external field acting on this object. And I want to consider a very special case first where this external field is uniform. Then we see that the total force, which is equal to Q times E external, that's the first one, minus Q E external, that's the force on the second one. And if I overlaid the forces here, I would have F plus. And remember, this is a negative charge, and that's why that force is in the opposite direction, F minus. And you can see that the sum of the total forces is 0. And so the center of mass will either stay at rest or move at a constant velocity. But there's still more. This will undergo a rotational motion because even though the force is 0, the torque on this object is non-zero. Now recall that when the total force is 0, then torque, which was defined as a sum, j goes from 1 to n, of rj cross fj, is independent of the choice of origin. So how can we depict that? Well, let's draw our objects again, plus and minus. And just to start with, this is a massless rod. And now you can see why we want a massless rod, because this object will rotate. And let's consider the center of mass. And we'll draw r plus, and we'll draw r minus. And we have F. We have E acting on this one, E external. But remember, the force is a little bit different. We have F minus, and up here we have F plus. So what we can see is that there will be a torque given by the cross product. And if we extend this vector r plus, we can see that this will produce a torque in the direction indicated by my thumb. Now, down here, if we extend this one in the same way, the torque there is in the same direction. So both of these objects both of the forces are exerting a torque on the same direction, and that will cause our object to rotate. Now remember, there's no total force on this object. The torque is independent of the point that we want to calculate. And we'll use that fact later on when we calculate specific examples. But for the moment, let's do a general calculation. We know that the torque is equal to the force, so that's Rj cross Fj, and the force is the qjth charge times the external field. And now, even though we only have 2 charges, I can make this an n charges in a system, provided that the total charge on this is 0. The total force, total charge is 0. So now, in a cross product, this is just a scalar quantity. It can be positive or negative. It's not a vector quantity, so you can move it around. And we're going to put it onto the first term, Qj, Rj, cross. Now, every single term in this cross product has the same uniform E field, which means I can pull it out of the vector sum of this sum over here. And if you recognize here, this quantity makes sense. Again, we're assuming that the total charge is 0. And then this is exactly what we called the dipole moment of the distribution of charge. And so we have the result that if we consider just a dipole, plus and minus, and remember, the dipole moment goes from the negative charge to the positive charge, P, and the whole system is acting in an external field that's uniform, then this dipole will undergo a torque. It will rotate, and it will rotate in that direction. Now, in summary, what we see now is for point-like objects, we can use our Coulombic expression. If we put that point object in an external field, it can experience a force. If the total force is 0, then the center of mass of the object will not accelerate. But if we have an extended object of 2 charges, then that object will experience a torque. And we have a very straightforward way to calculate that torque. One thing to keep in mind is when we get to examples is that, again, we're considering systems in which, in this calculation, the total force was 0.
So what we have here is an object that I'm going to turn into a dipole. This end, I want one end to become positive, one end to become negative, and I would like to see what happens to this dipole when it is in the large electric field that this Van de Graaff can make. So how do I do this? Well, first I get this ready, holding it against this stand like this, and then I turn the Van de Graaff on. And when the Van de Graaff is on, what is happening? The Van de Graaff is becoming positively charged, and that will induce a negative charge at this end and a positive charge at that end. The positive charge of the Van de Graaff is going to suck electrons from this side over to that side through the conducting rod of the stand. And now I'm all set. I'm going to turn the belt off while keeping the Van de Graaff charged. And I now have a dipole in an electric field. And if you watch, as I walk this around, the silver end is always being attracted towards the Van de Graaff because the silver end is the negative end of my dipole. It's swinging around a little bit, but if you notice here the silver end is towards the Van de Graaff, and if I come all the way around like this, when I'm over here, the silver end is towards the Van de Graaff again. And if I come all the way around here, the silver end is towards, now it's really swinging around, but you can see the silver end is being attracted towards the Van de Graaff. It's feeling a torque, which is trying to turn it so that the silver is pointing towards the Van de Graaff. If I go all the way around here, same thing. The silver is pointing towards the Van de Graaff. And now for fun, let's try and do it in the opposite direction. So I will discharge that, and I will put this back on the stand, but this time I will have the copper pointing towards the Van de Graaff. I want to show you that it is not the silver paint that's being attracted, it is actually the electric charge. So let's turn the Van de Graaff on. Now the Van de Graaff is charging up. The Van de Graaff is getting positive. That will be, this time it's going to make the copper end negative and the silver end positive. So I'm ready now. I will turn the Van de Graaff off. And this time I have my electric dipole in an electric field, and this time the copper end is attracted towards the Van de Graaff because the Van de Graaff is making the same field as before, but now I've changed the sign of my dipole. This time the copper end is negative, so it's the copper end that is being attracted towards the Van de Graaff. And if I walk it all the way around to the far side, it's always the copper end that's being attracted towards the Van de Graaff, always the copper that's being attracted towards the Van de Graaff. Last time it was the silver, this time it's the copper, because last time I charged the silver negative, and this time I charged the copper negative. So this gives you an intuition for the behavior of an electric dipole in an electric field. You can see that the electric field is making the dipole line up with the field, because if you think about the field lines coming out of this source of charge, the field lines are pointing out like this, and the dipole is lining up with them. There we go.